Hello, everyone. Nice to see you, and thank you for coming. So today we'll be talking about what's a honeypot, what it was built for, what the current popular honeypot projects today give us, and especially what we think they give us, but they don't. And just to do just to sync up, this is not going to be any, mapping thousands of keyboards and windows to get direct physical mappings for your Spring kernel shellcode. It's going to be not that advanced technically, but more on the methodological side. Okay, so I'm Dean. Next to me is Itamar, and the third guy who you can't miss is Gadi. And I'll just let him get the mic just to talk about what it is that we're talking about here, just to give the definitions up.
Thanks, guys. Thanks, Dean. So one of the things we did when we wanted to start doing this talk was, and again, this is not going to be, there's not going to be any shellcode, kernel shellcode or anything like that. This is just a more methodological talk. So if you're looking for that, leave. We will not, be hurt in any way. So we were asked, when we asked for feedback about this presentation, to explain what it is we're talking about. We just jumped into it and people said, wait, what is deception? I mean, we're used to the word cyber by now, right? We accepted it in a way, but what is cyber deception? What does it mean? So I would like for the next 5 minutes or so to go through this in the way of how we see it, and then connect it to the talk of honeypots, breaking them and making them. So cyber deception can be defined by many, many people. Our definition is essentially, we want to manage the attacker's behavior. Nothing more, nothing less. So that we can detect them, which is the first essential thing we're trying to do with many, security technologies. But the critical part is, which we'll try to show you, is with no false positives, or very low false positive rate, which is very critical. We want to be able to provide for investigation afterwards. And more than that, we want to be able to control the attacker, if not even start mitigating the attacker through this technology. So before we even start, as they say in academia, we sit on the shoulders or stand on the shoulders of giants. And back in the 90s, Fred Cohen worked on his deception toolkit, right? Lance Spitzner talked about honeypots, started the HoneyNet project. The HoneyNet project has its own line here because they deserve a lot of respect for all the work they have done to promote this field, to build open source projects on their own dime. So respect to them, and many, many, many others, all the way back to the book, The Cuckoo's Egg, in the 1980s. And of course, we can go all the way back in deception to Sun Tzu in ancient China or to the British in World War II. Just saying, we respect who came before us. So the critical aspect of this is really attackers or attacks. Solutions today in a way look for malware, payloads, vulnerabilities, and these constantly change. What doesn't change much, or by a very small delta, is the attackers. They work in a way by a certain decision-making process and methodology. And these generally remain the same. Some people call it the kill chain, other people call it something else. And there are many, many different approaches to this, but that is the critical aspect of it, because if we know for a fact, not what tool or vulnerability the attacker is going to use, but rather where the attacker is going to be, what is the next step in their decision-making process, we can wait there. We can, quote unquote, catch them. Or in other words, what we have, the advantage we have as defenders, is when an attacker comes into the network, usually, right, not for all operations, they don't know what's going on. A fog of war exists, they have no situational awareness. That is what we're trying to use against them. If we can productionize that, use that quote unquote vulnerability in their decision-making process, in their process in general, that is very powerful. So there is something called, some of you may know it, some of you may not, the OODA loop. It's a strategic decision-making process for tactical situations invented by Colonel Boyd in the 70s. And it's very, very simple. It's observe, orient, decide, and act. What I'm saying, and what we are saying, and what everybody who has done this before is saying, is essentially, if we can take over the first O, the observation. So when the attacker is trying to do something, for example, lateral movement, they see what we want them to see, and they believe what we want them to believe, and they proceed according to that. That is the win. That is what deception technology can give us. And this can come at anywhere along the route. It can come all the way early in reconnaissance and all the way out to exfiltration. Or in other words, this is what we're trying to say. Yeah, thank you for the courtesy laughter, a couple guys here. Appreciate it. There we go. Now, more than that, taking like 100,000 steps up and a mile high in the air, an abstraction. This is, in our view, an economic shift in how we do security. So let's consider how we plan an intelligence operation. Let's put ourselves in the shoes of an intelligence agency, a state-sponsored attacker, right? Let's say China, Russia, doesn't matter who right now, a cyber criminal. So you go through certain stages. For example, you do reconnaissance, intelligence gathering, right, what you're gonna do. You do scenarios planning. What am I gonna do if? How do I plan for this? Or even at the technological level, I'm gonna install Trojan horses on this machine here, my phone. What happens if the battery runs out too fast? So all across the way there. But eventually it comes down to one rule of thumb. It's a rule of thumb because it changes, but it always remains there somewhere. And that's, don't get caught. Basic, very, very basic intelligence operation. So for example, for the Chinese, many would say, it's what can I do until I get caught? So we talked about the intelligence operation, but what if you now knew something different? Think back, Stuxnet had code in it that was 12 years old. APT1, when they were disclosed by Mandiant, they disappeared for a long, long time after the tools were disclosed and were discovered by every antivirus out there, until they came back to full operations. Meaning, what makes a threat actor powerful, or one of the things anyway, that makes a threat actor powerful is the resources, Trojan horses, vulnerabilities, as opposed to a skitty, who just goes out there using whatever they can. We see some change in that, but generally speaking, that is their A game. Now, if you go back to the intelligence operation and you know for a fact now, after you planned it and you go and execute it and you don't want to get caught, or you want the window between getting started and getting caught to be as wide as possible, but now you know that every share you connect to, every computer you go to, every network you go through, every credentials you use, you could get caught. And getting caught does not mean attribution here, but rather losing your resources, losing your tool, so now every antivirus out there detects it. You're now nervous, you lose trust in your operation. And that is the economic change we're trying to do. So essentially it's like the song, every step you take, every move you make, I'll be there, right? If you know every step you take, you might get caught and lose your resources, that's an economic change which shifts the costs to you. So there are many, many elements of cyber deception. Building a cyber deception operation is complex, but every cyber operation out there, cyber deception operation out there, eventually comes down to one element that repeats itself. It could be a very, very small element, or it could be the main lion part of the operation, but that's the honeypot, the decoy, as we like to call it, because the honeypot means something very, very specific. It means lure the attacker in. It means usually low interaction, which can be fingerprinted, which is what this talk is about. So, doesn't matter, right, how the operation works and how the attacker actually got to the decoy, which is an entire other thing we want to talk about at another time. Once they do, consider this. Theoretically, if you control a machine completely, it's your machine. Nothing else should ever run on it except for what you put on it. If all of a sudden now new code runs on that machine, you know you caught an attacker. That's a 100% alert, single alert, you just caught an attacker. And that is the power behind deception. So the state of decoy technology is low interaction honeypots. It's not that high interaction honeypots are not there, but when you look at the world, and we did a scan of the internet, and we can show this. When you look at the world, this is what people use. Now, they're very, very useful for detecting automatic malware that scans the internet, some other scans. But when it comes to interaction with an attacker, interaction is a very, very loaded word, could mean many things. When it comes to an actual attacker catching a targeted attack, they fail, they fall short. They don't scale to different levels. And that's by design. That's how a low interaction honeypot works. They are limited by definition, and that is a recognized fact. So they emulate. So when you emulate something, it's not real, you can fingerprint it, which is where the talk starts. And they lure the attacker in. It's all in one. Now, high interaction honeypots on the other end, and this is just to clear the line to make sure we're all talking about the same thing before we get to the technology, right? Are fully instrumented forensic devices. That is how I personally like to call them. So potentially, I'm not saying every case, they would be real machines. As we said, everything runs on it, which is not ours, you will catch it. But they do not lure the attacker in. They watch. And the idea is generating more threat intelligence. So you can basically assist with the risk aspect of this. So a word about fingerprinting, and I'm almost done. This is critical because many of the guys here in this room and or will be watching this talk or are watching this talk, saying the word vulnerability is loaded. Is fingerprinting a vulnerability? If you connect to an Apache server and it says, hey, I'm an Apache server, is that vulnerability? I mean, it's not a shellcode, it's not an exploit. What's going on here? So what is the purpose behind the word vulnerability? Not necessarily the technical sense. So an OPSEC risk, for example, is that a vulnerability? If you look at Tor has some vulnerabilities over the years. And yes, a code execution vulnerability would be very critical for Tor, but a critical vulnerability for Tor, for example, is unmasking, de-anonymizing, being able to say, hey, that's an IP address for a real user behind Tor. So the purpose of a honeypot is something we discussed. If you can tell it's a honeypot, is that a vulnerability? I personally think yes, but the effect of the matter is this is the design and the state of the technology right now as it sits. So calling it a vulnerability is unfair, but then you look at the OPSEC of this and say, I can detect this thing. So it's a discussion to be had. Thank you very much.
Okay, so now let's get into more technical stuff of the lecture. And first, I'd just like to talk about what's the difference between a low and high interaction honeypot, okay? So a low interaction honeypot, this is probably everybody in this room already knows about, I'll go through it quickly. It's just simulations of networking services that you run in your network, and then if somebody talks to that network service that you haven't publicized and haven't been talking to anybody about, then by definition you know that something's gone wrong. Right? It's probably an attacker, but it could also be like a false positive in the honeypot sense where it's like a Nagios or something scan or Spiceworks where it's just auto backing up the network or something. But it's a very, very good concept of how to get attackers, right? And the way they just do it is they simulate some type of network service like SMB or SMTP or DNS or whatever. And the thinking is that if you write it yourself, it's very easy to monitor it, right? So SMB is like a very, very difficult protocol to parse. And for example, you can tell which folder the guy is trying to access if you've written the parsing yourself. It's much harder to do it if you're trying to understand the protocol Windows uses, right? Because it changes versions and it's very dynamic the way it works, right? High interaction honeypots are essentially getting the real system working, but then figuring out a way of how to monitor that network service or the things that the honeypot is servicing, right? And that's a very difficult thing to implement because then you're sort of walking in the path of regular security anomaly detection, right? Because you're trying to understand what's the bad thing and what's the good thing. So it's pretty difficult. And before we go into our work, I would just like to slightly discuss the previous work that's been made. Shodan does a website called HoneyScore. It's a honeypot or not website, and you just put in an IP and then it tells you if it's a honeypot or not. And when we just got to see it, when we were looking at previous research, we couldn't get it to make our honeypots look like honeypots. Like every single honeypot that we used, it would look like a real system on Shodan. So we didn't really understand until a later point what they were looking for, and then we realized that there's a honeypot that's a simulation of a SCADA system called Conpot, okay? And there's been previous research by the Shodan team and later on with more improvements by Sean Merdinger of how detecting Conpot, right? So the first thing they did was the name of the device was always the same. And then when people figured that out and started configuring it to be different, then Sean realized that the serial number is always the same. So if you go on Shodan and search for that serial number, you get like 10 machines around the world that are running that SCADA honeypot, right? And if you take that one of those IPs and run it in the HoneyScore, then you realize that it's a honeypot. So what we feel like, we haven't talked really to Shodan, but it's a really good start, but it's very incomplete in terms of detecting most of the honeypot projects. Okay, so the way we go through the projects individually is by layering on more and more complexity in terms of getting more stuff from the attacker and being able to collect more intelligence that will help you to mitigate. So the first one is the most basic one with the most simple ideas, and the last one will be the most complex one. So we'll start with artillery, And basically artillery is just a script that you can run on dedicated Honeypot machines or on your own machine. What it does is opens up ports that are very well known to attackers, like SMTP and DNS and SMB, and where all the attacks usually happen. And what it does is it just gives you this. So if you're telnetting into a SMTP mail server, it just acts very rudely, just gives you random data, and then it blocks your IP. And as soon as I started using this, I was like, this really reminds me of going up to a girl in a club and saying hi, and she's like, I have a boyfriend, and walks away, right? It's like really rude, but no, okay, thank you, courtesy laughs, thank you. So it's pretty obvious to detect, but artillery has a very basic concept, and that is just be able to block scanning and automatic exploitation and bots. And for that purpose, it works really well. But obviously, if you're a targeted attacker targeting that network, it doesn't really, it poses any difficulty to you. And another thing that's problematic with artillery, since the blocking happens without really actually interacting with the person talking to the service, it really depends on the spoofing protection in the network, but most networks don't have IP spoofing protection. Then you can use that to be able to block any IP you want. And that's a really problematic idea, especially if you're running artillery on your own machines. And it even works for the gateways. So by just sending 2 packets, you can just make every machine running artillery just drop from the network. But that's always assuming that you can do the spoofing part, right? So what can we learn from our artillery's work? That if you create a port that nobody should be touching, and somebody is touching, then that's an indicator of attacker's activity, and that's a nice way of blocking automatic malware or scanning attempts or whatever.
So can you hear me? So essentially, what we learn here as attackers, right, is leaving the technology behind, is Honeypot could be out there. Meaning now we as attackers need to start thinking, I'm connecting to something, could that be a honeypot? And that changes everything in the way we plan our operations. And that's something that we can see very, very clearly with artillery.
Okay, now we'll move on to bear trap. So bear trap says mostly the same thing as artillery, though it actually starts to implement the service that it's broadcasting. And one of the main ones that bear trap does is FTP. And one of the fails about bear trap is its default banner, which is configurable, but it just says bear trap. So if anybody knows what they're looking for, they already know that as soon as they connect it to that machine, that it's a honeypot, right? And another problem with bear trap, because we don't really like detection methods that are configurable, because then it depends on what the user does, is that when you try and talk to it on FTP before the authentication, it just returns 530 every time. And the thinking is, as soon as the user will pass in the login credentials, then we'll block that IP, and we also got his user credentials. And that's more interesting than just blocking random IPs, right? But that 530 problem is problematic, because FTP servers don't behave that way, right? If you try and, this is an example of VSFTP, that if you try and run commands on it before the login, it gives you output saying please log in, and when you're trying to do the login with errors, then it needs to specify what errors you're doing. So by just giving out 530 all the time, it's by definition not a real FTP service, and that's how you can detect bear trap, right? And also, bear trap also suffers from the same spoofing problems. You can also, if somebody is running bear trap on their machine, just sending them 2 packets and then they're off the network, or you can just block their machine from the syslog servers or whatever you want when you're trying to attack a network and using that to your advantage. Okay, so bear trap realized that you need to implement the service if you want anything interesting to happen against the attacker. And
you should do that one.
Okay, so what does the attacker learn once we learn about bear trap? It learns that you should be looking for indicators of deception, right? You shouldn't be just connecting to services and trying to see if they're, what I can get from them. First of all, you need to realize if there's indicators of deception like that bad error message or that banner. And now we come to HoneyD. So HoneyD is probably one of the most famous honeypots, and it's been a real change in the way deception has been made when it came out, and it's a really, really monumental work and very great in the world of deception. And what it basically says is it's a very, very configurable platform. You can decide which services you want to run and which scripts implement that service, and HoneyD comes with a set of default scripts that implement those services like DNS or SMB or FTP or SSH, right? And this makes it very, very difficult to be able to detect HoneyD because, for example, if somebody exchanged all their scripts or something they made in-house, then I have no way of being able to realize that if I'm an attacker. So that's a very good concept, but mostly people just use the custom, like the default scripts that come along with the HoneyD deployment. So, for example, here is the IIS service. In the first few lines, you see the code implementing that, and what they're trying to figure out is if somebody's trying to do a get on cmd.exe or dir or whatever, that's used to be a very common attack of trying to realize if you can get a shell execution inside the web server. And what happens is as soon as it receives this get request, it answers with exactly the same dir listing every time. Okay, and this is like pretty bad because you can really realize just signature this is a bad response, that this is a HoneyD IIS server. And also, it doesn't really make sense in a lot of ways. For example, if somebody is running the IIS HoneyD server as of today, that means they haven't changed their website in 15 years because the modified time of the www root is 2000, right? So it's a good idea, but if you're looking at does this make sense? There's a few issues with that. And also in the FTP strip on Linux, it doesn't support the DLE command, like the delete. So if you write down delete, it just says not implemented. And in the SSH service, it just doesn't do anything. It like opens up the port and lets you talk to it, but it doesn't even implement the service, right? So if an attacker is trying to exploit a machine, and he's like, I'm gonna run my 0 days on this, and it's really interesting to me, it becomes very obvious very soon to him that it's HoneyD. And just a possible fix, for example, for the IIS script is just randomize, just give an empty dir list and also randomize the byte counts and the serial number and all the timestamps, but do it periodically because, for example, some people have told me just randomize it on every request, but that's also very bad because if you request like 3-4 times and you see modified times that just run along the spectrum, then you're also realizing that it's a simulation, right? It's something to deceive you. So what can we learn from HoneyD's work? So when you're trying to implement the service that's deceiving the attacker, you should be doing it with no obvious indications of how it's a simulation, like there was in the previous projects we looked at.
So what essentially we can you hear me? So what essentially we can learn here, it's not just about banners like you saw earlier. When you implement this and you actually start conversing in a way as a service, it's got to be a real implementation. You can fuzz the thing and just see, hey, what's not implemented? And that's something an attacker will now have to do, but it's also an issue.
Okay, next up is Nova. So Nova is actually a management platform for honeypots. Gives you this cool user interface where you can do templated configs of machines that service honeypots, like for example, Windows machines and Linux machines, and then spin them up and spin them down and get really more high-level management of honeypots. And one of the issues in that was pretty interesting. So the default Windows config has the known NetBIOS service script, right? So if you're looking at the scripts that's implementing the services, it doesn't have a NetBIOS one, and Windows always have a NetBIOS one. And it would have made sense if the port was closed, because then maybe it's a firewall, but the port is open. So you're connecting to the NetBIOS port, and nothing is interacting with you as soon as you're talking to it. And this is a situation that doesn't ever happen on a Windows machine. It makes it pretty obvious that it's a Nova Windows config template, right? So one of the possible fixes is just implementing that service, or just even closing the port, so people won't figure out that it's a Nova Honeypot. And what we can learn from Nova's work is that implementing one service completely is also not enough. You have to have a set of services that make the machine look reasonable, make sense, right?
The main difference really here that we need to think from, let's just stop for a minute and think about the attacker. So we talked about services, right? We talked about going from regular ports to starting to implement them, making sure the implementation looks real at the very least, so you have to go through something. But now think about it, you're approaching a machine. Now that's an element by itself. Now if you all of a sudden see an IIS server and it's running FTP, or you see a Windows server and it's running something that the Windows server would never run, or it's lacking a service that Windows will always run, that is weird. That yells and screams honeypot. So when you run Nova, you have to be very, very careful about how you set up your machines, or the attacker will look at the whole and be able to tell, hey, that's a honeypot.
Yeah. So next up is Kipo, and Kipo is one of the cooler honeypots. What it does is, they call it a medium interaction, which means it actually does an SSH service fully that you can use against the machine. And this causes a lot of auto-exploitation stuff to be caught, because SSH is one of the more popular ones and lets you log into it very easily, right? So there's been some previous research on Kipo, and one of the ones we credit here is that it's very easy to understand you're in Kipo once you're in there, because not all of the SSH commands are implemented. Like, it's not actually a shell that you can interact with fully. And also, what they did was, which is very interesting, is they implemented wget. So what happens is when an attacker gets on an SSH machine, first thing they'll do is they'll download their payload or Trojan and run it so they can infect the machine. And what they're trying to do with this is get the wget to work and download the payload, but then the defender will have that payload and can protect themselves from it. But you can also use that wget for DDoSing or port scanning other machines, and they have currently no protection against that. And this is another cool way of detection that's previously been around. What happened was that Kipo, when it implemented the authentication protocol for SSH, what it would do is, as soon as there would be the key exchange, it would immediately try and do the client identification. And SSH protocol isn't built that way, right? The specification says that it's different of doing it that way. So it's very obvious when you're looking at the net capture of talking to Kipo that it's not a regular SSH service, and it's odd, right? And this has been in the past. And just another way of understanding how to fingerprint Kipo, when you're running the command uname -a inside of Kipo, it always gives you the same uname. That's something that we found. And it's pretty problematic. Like, if you would Google this uname, you would probably see people saying, I connected to this SSH machine and stuff is really weird. This is the uname, the details of the machine, and I have no idea of what's going on. So even people not trying to detect it outright are sensing that something is wrong, right? So a possible fix is to either give the actual machine's timestamp or just randomize it from a logical sense. And what we learned from Kipo is that a honeypot can be used as a tool not only for detecting, not just for saying you have an attacker and he used that IP, it's also for trying to start collecting forensic data, because that's the thing that will allow you to mitigate that threat, right? And essentially we see it when it's doing the wget or seeing which commands that attacker is running.
So this is a major shift in a way, when we move to medium interaction honeypots. Because again, we're talking about defensive technology, which is honeypots, but they interact in a way with the attacker. And the key issue here is you can start profiling the attacker. Essentially, now the attacker has two threats. Number one, the operation can fail, and not just fail as in, hey, I don't manage to connect to this specific box, or this specific honeypot, it's a honeypot, let's move on. The operation can fail. You're now interacting with the machine itself. So as simple as profiling your commands to saying, hey, I'm now blown, let's move away. And that's a major shift when an attacker plans an operation.
And next up is Do You Detect Anya. And Do You Detect Anya is one of the most interesting ones we've looked at because it actually gets the right way of getting as much information from the attacker in order to mitigate afterwards. And what it does is it actually runs something called libEMU that actually does an emulation of a machine, and it wants it to exploit against it, and then capture the exploit and see what it's doing, right? And it does this by servicing a number of services, and as soon as the machine is attacked, it runs it through libEMU. And Do You Detect Anya used to have a lot of problems with detection previously, and one of those, when you would run Nmap against a machine running, then it would just tell you it's Do You Detect Anya. And also, this is where we found an email from Marcus, which is a great guy, one of the creators of Do You Detect Anya, where he's actually, somebody's telling him, look, I found a few ways of being able to detect Do You Detect Anya. Can you fix these issues? And he says something that the low interaction honeypots guys have figured out a long time ago, but when you talk to people from the community, it's not very clear. And that is, he's saying, no matter how hard we try, low interaction honeypots will never be able to simulate a real machine, and the attacker will always have a way of detecting that is inside the low interaction honeypot. So I'm even not going to fix these issues, and you just have to understand that low interaction honeypots are just for a specific purpose, and that's stopping the low class of attackers. So how do you detect Do You Detect Anya? Do You Detect Anya services HTTPS, and the certificate that they give is their own certificate. It's just called, the issuer's domain is doyuania.carnivore.it. And even through other services, there's more ways of detecting Do You Detect Anya. One is that it allows anybody to connect to the FTP service, like any user, any password. And I haven't seen any real authentication system that lets the same user connect with two different passwords. So that's one way of detecting. Another way is that they didn't implement the DLE command in the FTP service. Right? So what can we learn from Do You Detect Anya's work is that we want to make the service exploitable to known exploits, right? Because if somebody's using an exploit and it follows their shellcode and their payload, we want to be able to give them the option of doing that, because then mitigation is very, very much easier to do afterwards, right?
This is really, really brilliant. Think about what you just said. Detecting the exploit. So going back to what we said originally, it's not just about saying, hey, I now have a connection to network that could be Nagios or Spiceworks. It's not just saying, hey, I have a real attacker here and they're interacting with it, let's alert. It's not just saying, I can blow their operation. Now it's saying I can blow their resources. I can get their exploit, their 0-day, the credentials they use. I can do something which will lead to attribution. And that is a whole other level. And that is why this tool took the technology so much further than it has been there before. It's not just about, hey, this is a cool thing. It's about saying, this particular person potentially attacked me, this country attacked me. It's about attribution. It's still a low interaction or medium interaction if you like Honeypot, so it's easy to fingerprint by design, but it's taking us to a whole other level operationally.
Okay, and next up is Glasstop, which is really cool. Glasstop is a honeypot which simulates a web app. So you run it, and then you get this website running, which has this number of exploit vectors that the Glasstop people want you to exploit, like LFI and RFI and other stuff that has going on. And what happens is when you run it, the default web page looks like this, and I'm sure anybody who's run Glasstop knows this. And it's like a weird template page, but they just give it off as a default when you're using it. And the thinking is that it's very configurable, and you can change anything in it. It has its own file system that it's simulating for the web app machine, and you can change any of the pages or the certificates that it's using, right? Like we said, and the footer of the page has this, this is a really great entry powered by nothing. And if you Google search for that string, it brings up a lot of interesting stuff. And one of those stuff, when we were doing it, was one of the top 500 websites online. It had a subdomain running Glasstop with that default page template, right? So running honeypots is very, very dangerous when you're just having the same default config and not realizing how to integrate it well into the thing you're running. And so one of the things that Glasstop catches is an LFI, and it just does it very, very promiscuously, right? So if you'll just do a query that has a question mark and then a directory traversal into etc shadow, it'll just give you, even if your URL isn't like, makes sense in a lot of ways, because it wants you to get that etc shadow or the other files that the user has put in Glasstop's simulated file system, right? But this creates a lot of problems. Like, since the user has access to etc shadow by regular Linux permission logic, he should also be able to access /proc, right? And /proc is a very problematic folder to try and simulate. Firstly, because you can go through the PIDs and see the actual processes running, and then find out if it makes sense that this is an actual web app machine that's running the app you're seeing. But at some point, for example, if you go into your own process ID that's running the web app and go into the memory maps of it, it's obvious at that point that you can figure out that it's a simulation. And if it's behaving accordingly to what you're doing against the web app, then the only way that they've been able to do it is to integrate an actual web app into it, and at that point it's no longer a honeypot, right? So this is a pretty more advanced way of detecting it. But when we talk to the Glasstop guys, they're saying, right, like we will never be able to implement /proc. This is a way we can't fix, right? Yeah.
Repeat the question. Repeat the question.
I would like if you could say that question for the end, so you could talk on the microphone. We'll hear you because we just didn't hear. Okay. Thank you. So a possible fix for that is just to disable permissions for /proc, but that raises eyebrows because it doesn't make sense in a Linux permission sort of sense, right? And what we can learn from Glasstop fork is let the attacker exploit the simulated machine fully. Like if Anya was just looking for the exploit in the shellcode, Glasstop with this virtual file system really wants to let the attacker like put in his own files or try and steal the user's intended fake files and see where it's being used, right?
The really cool thing about this is before we talked about the potential for attribution, the potential for taking the tools away. This is, of course, attribution can be about political situations. It's never just about IP addresses, but here attribution becomes real. Now an attacker needs to think not just about the machine and how it's built or what they do. They don't think about the entire operation. I can be identified if I do my job. If I go and work on these machines, if I try to do lateral movement, I can be potentially identified. And that changes the entire dynamics of an operation. How much effort you put into it, your cost of the operation, and that is brilliance of Lucas, really, when he puts it in. It still has the inherent limitations of the low interaction honeypot or medium interaction honeypot, but it takes us to a whole other level of making the attacker now think about this operation is at risk, as opposed to just my tool is at risk.
Yeah, okay, and last project we worked on is Kef Sensor. So Kef Sensor is a proprietary honeypot, and it's a really cool product because it lets enterprises use honeypots that aren't like an open source, something you have to configure and deploy with a lot of work. It's actually pretty simple to use it, and also we had a lot of fun working on it because every time, in the default install, every time Kef Sensor it runs this sound. Right, and then like this is giving us nightmares from the time we're working on this. The problem with Kef Sensor is that it doesn't really, the default config just runs all the services you can probably imagine. It also has a very, very low boundary of alerting, right? It also alerts on broadcast requests in the network So configuring it is very, very important to do it very accurately. And we also found ways of detecting Kef Sensor. For example, the HTTP service it's doing is just a default IIS server, and if you Google the exact page source code, you can find other Kef Sensor deployments. And also it does the same basic error with the HTTPS service, that it opens the port, but the port doesn't service anything. So if, for example, you're trying to browse to that in a browser, you'll get this website has a weird, this website SSL authentication isn't working, right? Which doesn't happen on a real web server. And also it has a configurable amount of concurrent connections that afterwards it blocks you away. So like Bear Trap and Artillery also suffers from the spoofing problem, that if you just send it false source IPs, then it will block you, and then you can choose which IP you just want to block away. So what can we learn from Kef Sensor's work is that when looking outside the open source community, even the proprietary products suffer from the same issues. Okay, now we're going to talk about how in the world honeypots are deployed. So what we did was a very specific scan, and that is we used the ZMaps projects. If you could just go online and go to scans.io, the ZMap project scans the web for different ports and different services periodically. And we just took the HTTPS scan in the 14th of July and looked for Ania's specific certificate, since you have the issuer string, just say Ania, right? And that's the only scan we did, but it shows like very interesting stuff, which I'll get into right now. Just a disclaimer, when we attribute the IP to an organization, the standard limitations apply, right? When you see the same IP being used by the same DNS name, same organization all the time, it's probably connected to their organization, but it could also have been a hostings website that at the time that we scanned it might have been a different website, but we really nailed down what we think is the right attribution to organizations, right? So this is what it looks like, and the ones at front are Taiwan and United States, which deploy the most Ania honeypots which are publicly exposed. It's very interesting to see the different numbers. Taiwan leads out by a far margin, and after the United States, it really drops significantly. There's some very interesting countries here. For example, a lot of countries in Africa that I wouldn't, I wouldn't imagine be running these types of honeypots.
Just a quick note, not necessarily the countries. For example, it could be different people deploying honeypots around the world to detect malware, right? Doesn't necessarily need to be that country. Naturally, attribution by IP is bad, right?
Yeah. And when we started looking at the organizations which we gave a declassified view of, you can see that most of the Ania deployments around the world are in a Taiwanese ISP, then in one of the United States universities, which are cool, I want to go study there or make my kids go study there. And then is another Taiwanese university, and one of the more interesting stuff we found is that one of the top cloud providers, we found a lot of IPs in that, and then we went into the range that they publish to show which IPs are in the range of the cloud service. Some of those IPs weren't in the range of the cloud service. So it might have been their actual corporate or the company's network that was running these honeypots. And also some very more interesting examples of organizations. You can see the Ministry of Defense for one of the European countries, one of the biggest international economic organizations, the US Municipal Authority, South African Financial Services Company, a lot of Taiwanese deployments of Ania, and even we got one malware research blog that had it in one of its subdomains as mx0. The blog's domain as if it's a mail server just servicing Ania. And one thing we didn't classify. Okay, so if you browse to oil.ir, that IP is in the same subnet as one of the Ania deployments. So what we went is we said if the HTTPS service is giving us the Ania certificate, what does it look like when you browse to the regular HTTP on port 80? And then we saw this. So later we figured out that one of the open source projects out there called the Modern Honey Network by ThreatStream packages a lot of different honeypots together, and when you're loading it, it shows Glasstop and Anya. So this is probably one of the cases where we just got the modern honey network. So lessons learned, and here we really tried and figured out how, based on the detection of those honeypot projects that we saw, how we would build the ultimate honeypot or the ultimate deception tool. And we just realized these flaws are easy, right? Nobody's technically impressed by what we showed here, and they are by design. Like Marcus said in his email, there's really no way to fix this. This will always be a problem. You can always detect low interaction honeypots. And you would never be able to capture or mitigate an advanced attacker through using honeypots. So what can we do to make a good deception tool from the lessons we learned from this honeypot, right? And here we sort of figured out a scheme of what the prerequisites are for making something be deceiving to an attacker in a way that you can get enough forensics to mitigate him afterwards, right? So first of all, you gotta supply the service, which artillery, for example, didn't do. It just gave random data. Then you gotta supply the whole service, like we saw on multiple occasions of different commands weren't being implemented. Then you gotta make the set of services make sense, like we saw in Nova, that though some services are genuine, it doesn't make sense for a whole machine to look like that if another service doesn't work that way. Also, we want to be able to get the attacker to succeed against us, because that's the best way of collecting forensic data that you can use to mitigate. So you want to make the services exploitable for known exploits. And obviously, the next stage is being able to make it exploitable to unknown exploits, right? And here we're really bordering on the line of if a low interaction honeypot can ever achieve this stage. Right?
So a really cool thing to mention, or important thing to mention at this point, is that a honeypot by itself, as we've seen it used in the 90s, for example, is something that lures the attacker in. What we're trying to describe is a machine that the attacker, for example, they're already on your network, if they also get there, we can catch them in the act, which is a major difference. We're separating the entire idea of a deception campaign or deception strategy or methodology from the honeypot. The decoy is a tool. And I remember I used to run a honeypot back in the early 2000s, and people would connect to me in a way we were afraid to lure them in, which was a methodological consideration we had to take in whenever we deployed the honeypot. And when you're actually considering the attacker is already inside, like everybody nowadays says, assume compromise, the attacker is already in, the breach already happened, you need to find it. The honeypot changes drastically. It's not about getting the attacker into the organization, it's about making effective detection and attribution, possibly, afterwards. And that is something that's really important to understand at this stage.
And the optimal situation and the fantasy is that the machine the attacker is attacking is an actual real machine that they'd like to attack, right? And this is just the way it looks like as a pyramid, and we really hope we'll be seeing the real machine solution very soon. We will be releasing code when responsible disclosure is concluded in 0x90.ninja. And we just really like to thank everybody who's been working on these projects, especially the HoneyNet projects and all the people who's helped us with the research. And here we have time for questions.
Yeah, but before the questions, it's really important to us. People have been working really hard with us. People use honeypots. This is not a disclosure of vulnerability. People use honeypots operationally. So we talk to a lot of people and try to coordinate with a lot of people to make sure people don't get hurt, and which is another reason why we're not disclosing code. So, for example, Lucas from Glasstop and all these guys. So I want to go through the names. I can't actually see them, to just read them out. I know it sounds lame, but it's important to us personally. I want to see him try to pronounce the European names, so.
I don't think we'll have time, but I think this slide is enough. I'd really like to leave a few minutes for questions. So. Yeah, go ahead. Yeah, if you can do the microphone, that'd be great.
Mm-hmm. But you separated firewall or VLAN somehow that it cannot touch any other part of the network. Can that be used as a honeypot? Has anyone tried with a real machine?
Of course, but then you're getting into the problem of monitoring, right? So how letting
can
know
monitor
stuff
it.
going on the machines.
You can build in
And also,
like
you need to lead the attacker into it, right? Why would an attacker be attacking it if it's just a
you can
static-
install some old operating vulnerable services or operating system, and
Yeah.
you can build in monitoring into it.
Yeah, that's true. Yes,
Have people tried?
yes, I agree. I agree. Yeah.
Any other questions, anybody?
Tar pets. I don't really want to go into something I'm not very knowledgeable about, so, no.
Other questions? Yeah.
Yeah.
So the honeypots can be identified. I would think that the downtime of the investors who interact with it will generate further.
So the problem here is that most of what these honeypots record is just an IP. And being able to know that there's an attacker in the network and getting its IP is very valuable, but it's very far from being able to mitigate advanced attacks. Right? Advanced attacker in your network will not be discouraged from using IPs that he's afraid of.
To be clear, we believe in honeypots, but more importantly, we believe in deception technology and methodology, which is why we're going through this and showing what works and how we can make it better. Does that make sense? Other questions? Well, in that case, I would also like to thank a quick thank you because we didn't go through all the names. Omer is sitting right here, who helped us out with the scans, and our partner Ran sitting right there, and everybody else. If you have any other questions and want to talk to us, please do. And thank you again to the Alinet Project and everybody else, Lucas, Marcus, everybody. And that's about it. What?
And thank you for listening.
Yeah, thank you for listening.